Okay, if you need to change forms, in this case, from intercept form to general form, that's pretty easy. General form is ax squared plus bx plus c. So general form, ax squared plus bx plus c. In this case, all you need to do is multiply this out, leave the 4 outside here, you get x squared plus 5x minus 3x minus 15. If you jump to this step, x squared plus 2x minus 15, I wouldn't mind. I might jump there. And then the last step is multiply that out, distribute the 4, and get 4x squared plus 8x minus 60. And there you are, general form. Notice the minus 60, and wasn't that our y-intercept? And then if you did negative b over 2a, you would get negative 8 over 2 times 4, which is 8, and you get that x equals negative 1. So connecting that information to the graph. This question is a little bit tougher, so we'll come back to that in a second. Sorry, here we are. This question, a little bit tougher, we'll come back to it in a second. This one, this one's good. How do you get to general form? Same way we got to general form last time. You just multiply this out. So following the order of operations, exponents first, so negative 1/2 times x squared plus 8x plus 16, and then plus 3. Now multiply by the negative 1/2, negative 1/2 x squared minus 4x minus 8, add the 3, and now we get negative 1/2 x squared minus 4x minus 5. Again, if you're looking at the graph, there's that y-intercept of negative 5. Opposite of b over 2a. That would be 4 over negative 1. And I think we had negative 4 as our value there. Easy to see in that one. Cool. Okay, a little bit tougher here. So I want you to rewrite this in vertex form, and I want you to do it by completing the square. So like we did in class, x squared minus 6x, throw the 4 to the outside. Completing the square is based on filling this out so that it is what we call perfect square, that it would be x plus or minus a number squared. So the way that works, if you want a more detailed explanation, a minus b quantity squared ends up being a squared minus 2ab plus b squared. A plus b quantity squared ends up being a squared plus 2ab plus b squared. What we're doing is we are presupposing, like we are forcing x squared minus 6x to be these first two terms. In this case, I'm dealing with this one because that's a minus and that's a minus. So I have x squared minus 6x, and that is supposed to be the exact same thing as a squared minus 2ab. So if x squared is the same as a squared, the only way that can happen is if x is equal to a. So now I have that these two terms are equal, and I know that a is an x. So look at what I'm saying. I've got this b and times 2, and that should be the same as 6. And that's why I take this 6, and I take what is 6 divided by 2. The reason I'm dividing by 2 is because that little 2 is right there. And that gives me a value of 3. What do I need to add to complete the square? Not b, but 9. I need to add b squared. So if I add a 9 here, that's illegal unless I subtract a 9 here. Now if you added all this up right now and collected like terms, 9 plus 4 is 13, and 13 minus 9 is 4. You would just get back to this, and you'd be running in circles. The reason we did this is so that now this thing in this box factors to x minus 3 quantity squared, and this out here is a minus 5. And now you're done. You're in vertex form. And if you go back and look at the graph, you would see this exact same idea, that you have a positive 3 as the x-coordinate of the vertex, a negative 5 as the y-coordinate of the vertex. You can see the the y-intercept of 4. But if you had to solve for the x-intercepts, this is a much easier equation to solve if you set it equal to 0. If I said 0 equaled x minus 3 quantity squared minus 5, add 5 to both sides, take the square root of both sides, plus or minus the square root of 5 equals x minus 3, add 3 to the other side, and I get that the x-intercepts would be 3 plus or minus the square root of 5. But guess what? I didn't have to simplify the square root of 20. I didn't have to deal with a 6. I didn't have to divide that whole mess. It was actually a lot easier because I knew how to complete the square. Alright, we did not go over a problem like this on Monday. This is the hardest problem when it comes to completing the square. So the problem with this is the 1/2. And the reason that's a problem is the way we complete the square, we can't have a half here. But luckily, I'm good at algebra, and I'm just going to rewrite this by taking the half out. And if I take the half out, I need to put a number here so that if I multiply by half, I would get a 3. Well, that's a 6. Good? And I'm leaving this 2 out here. So, if you multiplied in this 1/2 right now, I would get back to this right here. So I haven't done anything mathematically incorrect or illegal. All I've done is change the way it looked. And now I'm going to keep changing the way it looks. I'm going to look inside this parenthesis and I'm going to complete the square. So if you want a more detailed explanation of completing the square with something like this, back up the video a few minutes. I take half of 6. Half of 6 is 3, and I add a 9 here. Here's the hardest part. I didn't really add 9. I added 9 times a half. So if I'm going to add 9 times a half, I better subtract 9 times a half. Now we simplify. The whole reason I did this in here was so that the inside would factor to a perfect square. The 1/2 is coming along for a ride because it's still 1/2 times this whole thing. And now if I change this to 4 over 4 4 over 2 instead of 2, I get 4 minus 9 over 2. That's equal to minus 5 halves. And if you look at the graph, we had a vertex of 3, negative 5 halves. Good? Again, completing the square is why this stuff shows up this way. You are welcome to plug in negative b over 2a and plug that into this function to find f of negative b over 2a and use that as a way to check your answer. But I want you to know this algebra. I want you to know it. And I'll show you why in the video that you're going to watch for class today.